Nobody likes getting a shot. That sharp sting as the needle breaks skin. You can feel it coming, you tense up, and sometimes you look away. But when a mosquito bites you, you usually don't feel anything at all, not until minutes later when the itching starts. So how does a bug drill into your arm silently while a doctor's needle makes you wince? The answer isn't what you'd expect, and it's leading to a medical breakthrough that could change injections forever. The engineering problem. Let's start with what's wrong with needles as we know them. A standard hypodermic needle looks smooth to the naked eye. Under a microscope, it's a solid steel shaft, essentially a tiny metal pole with a beveled tip. When it enters your skin, it has to push through multiple layers of tissue, the epidermis, the dermis, and then into the subcutaneous layer where medicine gets delivered. That pushing motion tears through nerve endings. It's brute force penetration. Your skin is packed with nerve endings, especially in the dermis layer, where most injections penetrate. A typical hypodermic needle has a diameter between 0.4 and 0.9 millimeters, depending on the gauge. That might sound small, but at the scale of individual nerve fibers, it's massive. Each nerve ending the needle contacts sends a pain signal to your brain. The result? Pain every single time. Nature's design. Now let's look at what a mosquito does differently. When a female mosquito lands on your skin, and yes, only females bite because they need blood protein for their eggs, she doesn't just stab you with one smooth needle. Her mouthparts are far more sophisticated than that. Under an electron microscope, you can see that a mosquito has 6 separate structures in what we call the proboscis. 2 of them are the mandibles and maxillae. These are the saw blades. They're serrated with tiny teeth running along the edges like microscopic cutting tools. The other structures handle feeding and saliva delivery, but the mandibles and maxillae are what we care about. They're what break through your skin. But here's the critical part. The mosquito doesn't push, she saws. The mandibles move back and forth rapidly, vibrating as they work through your skin. It's a cutting motion, not a piercing motion. She's creating a path through tissue rather than forcing one open. Each individual tooth on those serrated edges is contacting less tissue than a smooth needle would, distributing the mechanical stress across many small points of contact instead of one large surface. Think of it this way. Pushing a baseball bat through a chain-link fence is like trying to force a baseball bat through a chain-link fence. Sawing with a serrated blade is like using wire cutters on individual links. One requires massive force and causes widespread damage. The other is surgical. The mosquito's mouthparts are also incredibly thin, far thinner than even the finest hypodermic needles. The labrum, which is the main feeding tube, has a diameter of roughly 20 to 50 micrometers. That's 0.02 to 0.05 millimeters. For comparison, that's about 1/10 the diameter of a standard insulin needle. The result is minimal nerve activation. Your pain receptors don't register the intrusion until the mosquito has already been feeding for several seconds, sometimes longer. By the time you feel the itch, which is actually an immune response to the mosquito's anticoagulant saliva, not the bite itself, she's often long gone. There's also evidence suggesting the vibrating motion may further reduce nerve sensitivity, though the exact mechanism isn't fully understood. What we do know for certain is that this sawing technique allows the mosquito to penetrate skin with roughly 50 times less force than a smooth needle would require. That's not an exaggeration. Studies measuring penetration force have confirmed it. The medical application. Engineers tried to copy this, but they hit a wall immediately. Mosquito mouthparts are made of chitin, a biological material that's both flexible and strong. Steel needles, even serrated ones, behave completely differently. They're stiffer, heavier, and more prone to breaking if made too thin. You can't just scale up a mosquito proboscis and expect it to work. The solution were piezoelectric actuators, materials that vibrate when electricity is applied. Engineers used these to create the back-and-forth sawing motion. The needle tips were laser-etched with microscopic jagged patterns that mimicked the mosquito's mandibles. The oscillation frequency was calibrated to roughly match what mosquitoes do naturally, high-speed vibrations in the range of hundreds of cycles per second. But it had to be precise. Too much oscillation and the needle becomes unstable. Too little and you lose the benefit. The frequency, amplitude, and serration pattern all had to be optimized. In human trials, subjects reported significantly less pain compared to standard smooth needles. Some felt almost nothing at all. The vibrating, serrated needle was creating what researchers described as a cleaner puncture, with less tissue deformation and fewer nerve endings activated. This wasn't just about comfort. For people who need frequent injections, diabetics testing blood glucose multiple times per day, patients on daily medication regimens, children receiving vaccines, pain isn't just an inconvenience, it's a barrier to treatment compliance. People avoid necessary medical procedures because they hurt. Kids develop needle phobia. Adults skip insulin doses. The technology is still being refined. Commercial products have been developed and are being tested in various markets. The needles remain more expensive than standard versions, and the vibrating mechanism adds complexity. But the core principle is proven. Mosquito-inspired design reduces injection pain. This is what biomimicry looks like in practice. Engineers didn't try to reinvent the needle from scratch using pure theory. They looked at a system that evolution had already optimized for millions of years. Mosquitoes have been penetrating skin successfully for at least 90 million years. That's how old the oldest mosquito fossils are. They evolved this serrated, vibrating approach not because they were trying to be merciful, but because it's mechanically efficient. It requires less energy, generates less resistance, and allows them to feed before being detected and swatted. We just borrowed the blueprint. Evolution doesn't design for elegance or human comfort. It designs for what works. When a biological system has been solving a problem successfully for geological scale times, there's usually something worth studying in how it does it. The mosquito's proboscis isn't just a tiny needle, it's a precision drilling system refined through millions of years of iteration. And now that same system might make your next shot just a little bit less painful. So the next time you slap a mosquito, remember, you're not just crushing a bug, you're destroying a surgical machine more advanced than anything in a hospital, a system that took 90 million years to build, refined across trillions of individual mosquitoes, each one a test of whether that design worked or not. We spent centuries trying to make needles less painful. The mosquito figured it out before humans even existed. Sometimes the best technology isn't the one we invent, it's the one we're smart enough to copy. And this is just one example. There are creatures out there solving problems we didn't even know we had. Organisms that can survive being frozen solid, insects that generate forces hundreds of times their body weight, animals that can see colors we don't have names for. Each one of them has something to teach us if we're willing to look close enough. Next time, we're going to look at something even stranger, an insect that hits so hard, so fast, that it doesn't just break its prey, it vaporizes the water around it, the mantis shrimp, and what engineers are learning from the most violent punch in the animal kingdom. But for now, if this made you see mosquitoes differently, even if you still hate them, hit the like button. Subscribe if you want to see more examples of nature's engineering that puts our best technology to shame. And drop a comment if there's a specific animal or adaptation you want me to cover next, because evolution has been running experiments for billions of years. We're just starting to read the results.